Hello everyone. So we now continue our discussion. So the previous slide I have presented is this one. Okay. So we ended up here and we now proceed with our next topic called problem solving on test of hypothesis on two means for paired observations. Okay. So so here's the problem. No. So we have blood sample data in a study conducted in the Forestry and Wildlife Department at Virginia Tech. J.A. Wesson examined the influence of the drug succinylcholine on the circulation levels of androgens in the blood. So blood samples were taken from wild, free-ranging deer immediately after they had received an intramuscular injection of succinylcholine, administered using darts and a capture gun. A second blood sample was obtained from each deer 30 minutes after the first sample, after which the deer was released. So the levels of androgens at time of capture and 30 minutes later, measured in nanograms per milliliter for 15 deer, are given in time of injection, are given in the table. Assuming that the population of androgen levels at time of injection and 30 minutes later are normally distributed, test at the 0.05 level of significance whether the androgen concentrations are altered after 30 minutes. Okay, so this is the problem on test of hypothesis on two means for paired observations. Okay, when we talk about paired observations, so I'm referring to a certain sample. Okay, let's say we have uh, in this example we have 15 deer. Okay, now as you notice here, there is what we call as there is at time of injection, as stated, the levels of androgen was measured, no? So at time of injection, at time of capture, or at time of injection, okay, the levels of androgens at time of capture and 30 minutes later. So there is now measurement, no? In nanograms per ml. So we have two observations now. So observation one, we have a time of capture. Okay, for deer one, let's say for deer one, we have 15 deer. We have deer number one at time of capture. What is the levels of androgen of that deer at time of capture or at time of injection? Okay, so and then we have another observation 30 minutes later. Levels of androgens was measured. Okay, so level of androgens was measured, and in that case, we have another observation, no? Another nanograms per ml. So we have two observations now, and we call those observations as paired observations. Okay, so because it refers to a certain deer, no? So for every deer, we have paired observations, no? So for every deer, we have paired observations. Okay, we have data at time of capture, another data 30 minutes later for every deer. So we have now 15 paired observations. We have here 15 deer corresponding to 15 paired observations. Okay, so we now proceed. Now, let's analyze the problem. So here's the problem. So here's dir 1 up to dir 15. So at time of injection or at time of capture, the level of androgen in the blood, okay, for dir number 1 is 2.76. 30 minutes later, it rises to 7.02 nanograms per ml. So there is an increase at the level of androgen in the blood by dir number 1. However, for dir number 2, as you notice, there is a decrease. For dir number 3, there is an increase. Okay, for dir number 4, there's an increase. Dir number 5, there is an increase. And so forth. No? Now, as you notice, there's an increase in the androgen level for most of the deer, no? There's an increase in the androgen level, okay? So for deer number 10, there's a decrease. But mostly, there's an increase, no? So this is the experiment that was performed, no? Okay, so what is our goal? Okay, let's go back to the previous problem. Our goal is to test at the 0.05 level of significance whether the androgen concentrations are altered after 30 minutes. So after 30 minutes of injection, uh, does androgen concentration in every deer significantly altered? So that is we're gonna find out whether it is significantly altered or not. So we have to formulate our null hypothesis and alternative hypothesis based from the problem. Okay, so let's go back. So analyzing this, so we have 15 observations, 15 paired observations. Okay, we have 15 deer corresponding to 15 paired observations. No? And our assumption no, is this. As stated in the problem, the assumption is the population of androgen levels at time of injection and 30 minutes later are normally distributed. No? So meaning the graph is a normal distribution at time of injection and 30 minutes later. So this is the level of significance that was stated in the problem. And we're gonna find out if the two means are not equal. Okay? Mu sub 1 not equal to mu sub 2. Okay? This is at time of injection. Okay? Androgen level. Now, population of androgen level average or the mean. The mean of the population of androgen level at time of injection. We are gonna compare it with the mean population mean of the population of androgen levels after 30 minutes of injection. No? Now, we're gonna determine whether they are not equal. No? Okay? So, we proceed. So, in this case, we have mu sub 1 not equal to mu sub 2. So, we have mu sub 1 minus mu sub 2 not equal to 0. Okay, we can able to transpose to the left side of the equation. And note that mu sub 1 minus mu sub 2 is equals to mu sub d. Okay, so the difference between two means denoted by mu sub d. Okay, the difference between the two mean population, no? So we have mu sub d. So we have now the null hypothesis, okay, formulated as mu sub d equals to 0. How come it is 0? Because we're going to determine whether the level of androgen in the blood for the deer, for every deer, was altered, no? So that is our goal. So let's go back. So test at the 0.05 level of significance whether the androgen concentrations are altered after 30 minutes. So therefore, the null hypothesis is that it's not altered, it's not changed, right? So if it is not changed, so therefore there's no difference. The difference is 0 between the two means. Okay, so that will be now our null hypothesis. And we're gonna test that null hypothesis. So for the alternative hypothesis, are altered after 30 minutes. For the alternative hypothesis, since it is altered, it can be lower or higher, no? So that means it could be greater than or less than. No, the difference could be greater than 0 or less than 0. Okay? So therefore, that's two-tailed test. We're gonna use two-tailed test. Okay? So we proceed. So this is d sub 0. Okay? So mu sub d, so it's not equal to 0. So it could be greater than or less than 0. Okay? So this means that after 30 minutes, level of androgen, okay, for every deer is altered. Okay? In general. So in general, no, level of androgen in the blood of every deer is altered. No? So in this case, we use alpha equals to 0.05. So this is step number 3. For step number 4, what test statistic to use? And we will establish the critical region. What test statistic to use? So let's analyze. No? So let us analyze. Let us go back to the original problem. So as you notice, we have here paired observations. No? We have paired observations. And in that case, we're gonna use use the table I have shown before. Okay, so I think this is the one. Okay, so for paired observations, here, for paired observations. So for paired observations, this is the null hypothesis. Mu sub d equals to d sub 0. Okay, so mu sub d equals to d sub 0. Okay, and this is this is used for paired observations. And then we have here the formula for the test statistic. So we will use t-test, no? We'll use t-test. Okay, and we have the number of degrees of freedom. Okay, and then we have d bar. Okay, so later I will show you on how to find the value of d bar. No, okay. So then d sub 0 in our example, this is equals to 0. Okay, So we're gonna test if mu1 is equals to mu2. If mu1 is equals to mu2, that is mu sub 1 minus mu sub 2 equals to 0. And that's d sub 0. Okay? And this is now mu sub d. Okay? For the alternative hypothesis, h sub 1, so this is employed. Mu sub d is not equal to d sub 0. No? Because of the word altered. Okay? In the problem, the word altered is used. So this denotes that there is a change. And that change could be greater than 0 or less than 0. No? So we will have two-tailed tests. Okay? And then where this will now be the critical region. So t less than negative t alpha over 2, t greater than t alpha over 2. Okay? So let's go back to the problem. Okay, so we have this one. No, not this one. This one here. So we're gonna use t-test, and we have two-tailed tests. No, we have two-tailed tests, and this is now t sub alpha over 2, and this is negative t sub alpha over 2. So this is alpha over 2 equals to 0.025, because alpha in the problem is 0.05 divided by 2, so this is 0.025. So this area is about 0.025 square unit. No? Likewise, the left area is also 0.025 square unit. Okay? And below this value, negative t alpha over 2, okay, that is the critical region. Another critical region above this value or higher than this value or greater than this value, t sub alpha over 2. So we have to identify the t value. No? The critical value of t. No? Critical value of t. Okay? So we can able to find out this using table A.4. Okay? Using table A.4, we can able to find that value. So we have to determine the number of degrees of freedom. Okay? So in this case, the number of degrees of freedom by formula is equals to n minus 1. Okay? So let us verify if it is really n minus 1. So from the table, yes, this is the formula for the number of degrees of freedom for paired observations, n minus 1. So we proceed. So n minus 1 is 14 now. We have 15 there, minus 1, we have now 14. So the number of degrees of freedom is now 14. So we can now use table 8.4 because we have now alpha over 2, 0.025, and 14. Okay, so with that, this value is 2.145 using table 8.4. On the other hand, by symmetry of the graph, this is negative 2.145. Okay, so let us check using table 8.4. So let us check using table 8.4. Okay, so here's table 8.4, and we have So if we have alpha over, so we consider area to the right. So this alpha over 2 is equal to alpha here, now in the table. So we shall search for 0.025. So alpha value in the table of 0.025. Okay? Take note, not 0.05 because we have two-tailed tests. For two-tailed tests, we consider half of 0.05, which is 0.025. Okay? So this is 0.025, and the number of degrees of freedom is 14. So searching for 14 degrees of freedom. There, here, we have 2.145. So that's why this is now 2.145. So 14 degrees of freedom, alpha of 0.025 in the table, but in the problem, it's alpha over 2, no? So this is 2.145. Okay? So that's it. And then here's the formula for the test statistic computed value. So as I have shown, we have t equals d bar minus d sub 0 over s sub d over square root of n. So this can be found. So this can be found where? In the table I have shown. So let's check again. Here we have t equals d bar minus d sub 0 all over s sub d over square root of n. Okay, so we now proceed. So this is the table. Okay, at time of injection and 30 minutes after injection. So we'll get the difference of the two. Okay, so we have at time of injection and 30 minutes after injection. So we have 2.76 minus 7.02. Okay, so we have negative 4.26. No? Okay, 5.18 minus 3.1, we have 2.08. No? We have 2.08. No? Okay, and then 2.68 minus 5.44, we have negative 2.76, and so forth. No? So it's so we have the difference of the two. No? Now we proceed. No? This d, given this d for every deer, no, d value, the difference, we'll get the average of the 15 d values, and that is now d bar, the mean. Okay, the mean difference. So we'll solve for the mean difference. Okay, and using calculator, we can able to solve for the mean difference. No, so let's see what is the mean difference. Okay, what's the mean difference? Okay, mode statistics. So let's solve for the mean difference. So we have negative 4.26. Okay, then 2.08, negative 2.76, negative 0.94, negative 1.11, negative 3.21, negative 7.31, negative 13.74, negative 0.52, 2.45, 0.68, 0.16, negative 68.03, negative 26.55, negative 24.66. Okay, then press AC, shift 1, then we have 4, press 4. So we have X bar, you press X bar for D bar. So D bar is negative 9.848. Let us check. So we have negative 9.848. There you have it, negative 9.848. Then you indicate the unit, nanogram per ml. So as shown, we have androgen level na in nanogram per ml. Okay? And then the standard deviation of the sample, S sub D. So shift 1, 4 again. Press now 4 for SX for the standard deviation of the sample. So this will give us 18.474 nanogram per ml. Okay? And then we can now compute for the t value. Okay? The value of the test statistic is negative 2.065. So this is 9.848 nanogram per ml. No? So this is 0. So that means there's a difference between the two, the androgen levels. Okay? But is this significant? Is this value significant? The D bar is D bar value significant? No? To reject that the two population means are equal? Okay? Is this value significant for us to say that there is no change in the androgen levels, no, at the time of injection and 30 minutes after injection? Okay? So let us check whether it is, so let us test whether this value is significant or not, negative 9.848. So what the t value obtained is negative 2.065. So this is, so take note, this is square root of n, total number of years 15. Okay, then standard deviation 18.474. So let's just determine negative 2.065 whether this value is in the critical region or not. So let's go back to the table. So negative 2.065, as you notice, it is in the non-rejection region. No, it is in the non-rejection region. It is not in the critical region, in short. Okay? Negative 2.0 something. Okay? So that's why we can now conclude that since the computed value t equal to negative 2.065 is not in the critical region, therefore do not reject the null hypothesis. Thus, at the 0.05 level of significance, androgen concentrations are not significantly altered after 30 minutes. No? Androgen concentrations are not significantly altered after 30 minutes. In general, we can say that they are still equal. No? The androgen level, androgen concentrations, no, before at the time of injection and 30 minutes after injection are equal. No, they are equal. Okay, because in our tests it shows that it is not significantly altered. No, androgen concentrations are not significantly altered. No? After 30 minutes. So that's it. No, I hope you get it. So we now proceed with our next topic. Hypothesis test concerning variances. Okay, so for variances, in testing hypothesis, we're gonna use the following. No? For constructing the null hypothesis, we have sigma squared equals sigma sub o squared. For constructing the alternative hypothesis, no, sigma squared less than for one tilde test, for another one tilde test, for two tilde tests. Okay, then the critical region. So I will discuss this in detail when we proceed with an example. Okay, so in here for variances, if this is our null hypothesis, so we will use the chi-squared statistic. No? So this our test statistic now is chi-squared. So therefore, the distribution is the distribution of chi-squared, no, is a chi-square distribution. No, the distribution of this value, no, the distribution of this statistic is a chi-square distribution. So then we have also comparing the two variances for population 1 and population 2. So if you are to compare the two variances for the for the null hypothesis, sigma 1 squared equals sigma 2 squared. Okay, so we're gonna use F distribution. No, so we're gonna use F test. Okay, our test statistic is F. Okay, if we are to compare the variances of two populations, no, and then I will discuss this in detail when we have some example. No, okay. So for the chi-square distribution, okay, so you know this already. I have already introduced this before. Okay, for the F distribution. So let's answer an example. Problem solving on test of hypothesis on a single variance. So here's a problem. A manufacturer of car batteries claims that the life of the company's batteries is approximately normally distributed, with a standard deviation equal to 0.9 year. If a random sample of 10 of these batteries has a standard deviation of 1.2 years, do you think that sigma is greater than 0.9 year, considering the value of the chi-squared statistic? Use a 0.05 level of significance. So let us analyze. So given, so the claim is the standard deviation is equal to 0.9 year. Okay, so as stated here, no, a manufacturer of car batteries claims that the life of the company's battery is approximately normally distributed with a standard deviation equal to 0.9 year. So that is the population standard deviation now. 0.9 year denoted by sigma. If a random sample of 10 of these batteries, so we have now n equals to 10 as our sample size, has a standard deviation of 1.2 year, no? So the standard deviation for the sample, okay, for 10 batteries is 1.2 year. Now, do you think that sigma is greater than 0.9 year, considering the value of the chi-squared statistic? Now, we will find out the value of the chi-squared statistic. And is sigma greater than 0.9 year? No, considering the value of the chi-squared statistic. Okay? So as you notice, this is the population standard deviation, 0.9 year. And then, we get a sample consisting of 10 batteries. And the standard deviation results to 1.2 year, which is higher than the population standard deviation, which is the claim. So we are to test the claim whether it is really 0.9 year. No? So getting this value of 1.2 year, we're gonna solve the chi-squared statistic value. And from that chi-squared statistic value, we can decide whether to reject or not reject the claim that the standard deviation is 0.9 year. Okay, so let's continue. So we're gonna test it at the 0.05 level of significance. So here's the null hypothesis. So take note that what is given in the problem is standard deviation. So we have to convert the standard deviation to variance, no? In order to obtain the chi-squared statistic value. Okay? So we're gonna use the uh, we're gonna square the standard deviation, no? And so that it will be converted to variance. So as you notice in my in the table I have shown, okay, what is being compared are variances, right? So sigma squared equals sigma 0, sigma sub 0 squared. So variances are compared and not standard deviations. So we have to adjust, no? We have to convert standard deviations to variances. Okay? And this is the formula for the chi-squared statistic value, no, that we will use later. Okay. So sigma squared 0.81 square year. So as you notice, sigma is equals to 0.9 year. We have to square 0.9 year. So that is 0.81 square year. No? So that is now our null hypothesis that the variance is 0.81 square year. For the alternative hypothesis, we have sigma squared greater than 0.81 square year. How did we arrive at that value? So there's a question. Considering the value of the chi-squared statistic, do you think that sigma is greater than 0.9 year? Okay, so that is now the alternative hypothesis. No? So that we have to convert it first to variance so that it will be alternative hypothesis. So sigma squared greater than 0.81 square year. Okay, then the level of significance is 0.05 as stated in the problem. So we have test statistic is what test statistic? Chi-squared, as I've shown, no? And the critical region. So this is the graph of the chi-square distribution. Okay? And alpha is 0.05, right? This alpha value, so this is area to the right. And area to the right is simply alpha. And alpha is 0.05. And we are to determine the number of degrees of freedom. Okay? So what is n in our problem? N is equals to 10. 10 batteries. So minus 1, we have 9. Okay? So using table 8.5, we can able to determine the value of chi-squared sub alpha. And that is 16.919. So we can check. Is it really 16.919? So table 8.5. So table 8.5. So alpha is 0.05. So alpha is 0.05. Okay, so here 0.05. And V is 9. Okay, V is 9 there. So alpha 0.05, V is equals to 9. That is 16.919. Okay, so that's it. Now we proceed. So we have to determine the value of the chi-squared statistic. So by formula, chi-squared is equals to n minus 1 s squared over sigma sub o squared. No? So this is n is 10. The standard deviation, no? The sample standard deviation in the problem is 1.2 year, right? It's 1.2 year. And this is the sigma sub 0 squared, 0.9 year. So sigma sub 0 is 0.9 year. So let's go back to the previous slide. So this is here. So sigma squared equals 0.81 square year. This is sigma sub 0 squared, no? This is sigma sub 0 squared. Okay? So this is also sigma sub 0 squared. Okay? Okay, so that's it. Okay? So that is 0.9 squared, that is 0.81. Okay? And we get 16. Okay? Now, what is our decision? We get 16. 16. Is 16 in the critical region? No, it's not. It's below the value of the critical region. It's below the value of chi-squared sub alpha, no? So the critical value of the test statistic is 16.919, and our 16 is less than 16.919. So we can conclude that we are not to reject the null hypothesis. No? So let's now proceed. Since the computed value chi-squared equals 16 is in the non-rejection region, or it is not in the critical region. No? Do not reject h sub 0. Thus, sigma is not greater than 0.9 year, considering the value of the chi-squared statistic. No? So that is our conclusion now, that sigma is not greater than 0.9 year. No? Kasi nakuha natin 1.2 year dun sa sample. Sapat na ba yon para masabi natin na greater than 0.9 year yung standard deviation ng population? So, lumitaw sa test natin na hindi. No? So, therefore, tatanggapin pa rin natin yung claim na 0.9 year yung standard deviation ng population ng batteries. No? Okay. So, that's it. So, we can proceed. So we have here problem solving on test of hypothesis on two variances. Dalawang variance naman. So in testing for the difference of the abrasive wear of the two materials in test of hypothesis on two means unknown but equal variances, example, we assume that the two unknown population variances were equal. Were we justified in making this assumption? Use a 0.10 level of significance. Okay, nag-solve na tayo ng dati ng problem nito, no? So, ngayon, pakita ko muna yung problem. So, pero bago ko pakita, iti-test natin kung equal talaga. Were we justified in making this assumption? No? Kasi inassume natin dun sa problem that the two unknown population variances were equal. Okay? So, ito yung problem. An experiment was performed to compare the abrasive wear of two different laminated materials. 12 pieces of material 1 were tested by exposing each piece to a machine, measuring wear. 10 pieces of material 2 were similarly tested. In each case, the depth of wear was observed. The samples of material 1 gave an average coded wear of 85 units, with the sample standard deviation of 4. While the samples of material 2 gave an average of 81 with the sample standard deviation of 5. Can we conclude that the 0.05 level of significance, that the abrasive wear of material 1 exceeds that of material 2 by more than 2 units? Assume the populations to be approximately normal with equal variances. So our assumption here is that they have equal variances. Were we justified? No? So, we have to determine, no? So, were we justified in making this assumption that the two are equal? The two variances are equal, no? Equal variances as stated, right? Okay, use a 0.10 level of significance. So, alpha now is 0.10. Okay? So, we proceed. Alright, so we have the following data, no? So we might use them later, so it depends, no? We already solved this problem, no? So this is now our null hypothesis. Sigma 1 squared is equal to sigma 2 squared. Okay? Sigma 1 squared is equal to sigma 2 squared. And our alternative is that they are not equal. Why is it not equal symbol, not greater than, not less than symbol? Because of the word, because it is stated here that, or there's a question here, were we justified in making this assumption? Okay, so that means that it could be greater than or less than, no? Were we justified in making this assumption? So therefore, we used the not equal sign symbol, no? Okay, so this is our alternative. And now the level of significance is 0.10. So what test statistic to use and what is the critical region, no? So where is the critical region now? So let us determine. So let me illustrate. So we are comparing two population variances, right? So we are comparing two population variances. So if that's the case, this will be used. Sigma 1's this null hypothesis of sigma 1 squared equals sigma 2 squared. So we will use the F test statistic, no? So F test statistic, okay? So we will have an F distribution here. So F test tayo, F test. Okay? So this is the formula for finding the value of F. Okay? And then two-tailed test tayo, not equal sign. No? Two-tailed test tayo. Okay? So let's go back now. So we have two-tailed tests, okay? And this is alpha over 2. Kasi ang alpha natin ay 0.10. So this is 0.05. This is also 0.05. And this is now f sub alpha over 2 v1 v2. Okay? This is f sub alpha over 2 v1 v2. So take note, pag f-test, may dalawang degrees of freedom na kino-consider dahil meron tayong dalawang population, no? Na kino-compare, di ba? So therefore, magkakaroon ka ng dalawang sample. Okay? So, and then, ito naman. So if this is alpha over 2, this is 1 minus alpha over 2. No? F sub 1 minus alpha over 2. Okay. So take note, paano siya naging F sub 1 minus alpha over 2 yan? So this is area to the right. Itong F alpha over 2, area to the right yan. No? This is alpha over 2. Ngayon, yung 1 minus alpha over 2, no? So, ibig sabihin, ito yung sakop niyang area. 1 minus alpha over 2. Area to the right din siya. Pati yung sakop na area nung f sub alpha over 2 kasama. Okay? So, ibig sabihin yan, ito ay, ang area na yan ay 1 minus alpha over 2. Itong area na to na nasa left, alpha over 2 lang. So, pag pinag-add mo yung dalawa, 1 minus alpha over 2 tsaka alpha over 2, magre-result sa 1. Cancel. So, 1 equals 1. Right? Magre-result sa 1. Sabihin niyan, 100%. Okay? Sabihin niyan, 1 ang total area. So, tama na nga naman. 1 ang total area talaga niyan. Equal to probability of 1. No? Equivalent to a probability of 1. Kasi ano yan eh, continuous probability distribution, di ba? Okay, so we can now proceed. So we have v sub 1. So paano naging 11? Okay, balikan natin. Ito yung given sa problem kasi. Meron tayong 12 pieces of material 1. 10 pieces of material 2. So, 12 minus 1, 11 degrees of freedom. Ito naman, 9. Okay, 9 degrees of freedom. Okay? So, yan yun. Kaya 11 tsaka 9. Okay? Ayan. So, dahil alam natin to, tsaka yon, ito ay, ang sagot ay using table 8.6. Okay, 11.9. So, ang sagot niyan ay, so, kung mapapansin nyo, may dalawa siyang sagot. Meron tayong pinag-add na dalawa over 2. Bakit kaya? Okay, pakita ko na. Sige. So, bakit kaya ganon? Okay, so, table 8.6. Okay, we have, so ang alpha over 2 na to, sa problem, ay yung alpha sa table. Okay? 0.05. So, ito yon, ito ay 0.05. No, yung alpha over 2, 0.05. Then 11.9. 11v1. 11v1. So, kung mapapansin nyo, walang 11 na v1. 10 tapos 12 na. 10, 12. Meron bang 9 v2? Meron bang 9 na v2? Ayun, meron. V2, 9. 11, wala. V1 na 11, wala. So, therefore, sa gitna ng 3.14 at 3.07, kaya pinag-add natin sila, divide by 2. We get the average. No? Kasi wala eh. Wala siya. No? So, walang exact value sa table. Yun ang limitation ng table. So, we have to adjust. So, add natin, divided by 2. We get 3.11 as the answer. No? Okay? On the other hand, ito naman, f sub 1 minus alpha over 2. Okay? V1, V2. So, ang 1 minus alpha over 2 ay 0.95. No? E kaya lang sa table 8.6, no? Sa table 8.6, wala tayong 0.95. Ang meron lang natin, 0.05 at 0.01. So, i-convert natin yung 0.95 in terms of 0.05. No? Convert natin. So, tinuro ko na dati yung formula kung paano gawin yan. So, ang gagawin natin, so apply lang natin yung naturo ko sa chapter 4. Kukunin natin yung reciprocal. 1 over f. So, tapos, yung 0.95, iwa 1 minus natin. 1 minus 0.95, yun ang 0.05. Tapos, magpapalit yung position ng 11 and 9. Magiging 911 siya. Okay? Yung V1, V2, okay, magpapalit, magiging 911. So, meron ka na ngayong bagong V1 at bagong V2. Okay? So, 911 na siya. So, tignan natin sa table kung merong value yon. 0.05911. Tignan natin. 0.05. Okay? 911. Tignan natin. 911. 0.05. Okay? V1, 9. Oh, merong 9. Yes. V1, 9. V2, 11. 0.05, no? Ayun, 2.90. V2, 11. V1, 9. V2, 11. 2.90. Okay? So, 1 over 2.90 is 0.34. So, yun ang sagot. No? So, 0.34. I hope you get it. No? Okay? So, we proceed. No? So, So, the value of the test is statistic. Setting value ng F. So, base yan dito sa pinakita kong table. Ito. F equals S1 squared over S2 squared. Okay? Okay? So, ang S1 natin ay 4, ang S2 ay 5. So, saan natin nakuha yon? Bakit nagkaroon ng 4 and 5? Ito yon. Yung previous example kasi, meron tayo ditong ito, with the sample standard deviation of 4. Ito, S1 equals 4 units. Tapos, yung isa, with the sample standard deviation of 5. S2 equals 5. Okay? Ito yung sample, 4 and 5 sila. Pero, yung population, variance, okay, inassume natin na equal. With equal variances. Okay? So, 4 ito, 5 yon. Ngayon, kung 4 ito, 5 yon, okay, were we justified now na pinag-equal na inequate natin yung dalawang population variances? Kasi yung sample variance, yung dalawang sample standard deviation hindi equal eh. Pero hindi ba significant yung hindi sila equal? Okay? So, hindi ba significant or significant yung dalawa? Significant na ba yung dalawang value na to para masabi natin na yung dalawang variances ng population ay hindi equal? No? Okay, so tignan natin ang sagot. So, 0.64 ang sagot. So, S1 is 4, S2 is 5. So, ang sagot natin ay 0.64. Okay? So, yung 0.64 na yan, so pwede na tayo mag-decide. Is it in the critical region? 0.64? Let's see. 0.64. 0.34, nasa between 0.34 and 3.11 non-rejection region. So, ibig sabihin, not in the critical region. So, ibig sabihin, wala siya sa critical region. Diba? Ang kasing nakuha natin ay 0.64. So, kung 0.64 ang nakuha natin, wala siya sa critical region, no? So, wala siya sa critical region. 0.64 is in between 0.34 and 3.11. It's not in the critical region. Therefore, do not reject h sub 0. So, do not reject h sub 0. Therefore, we were justified. Diba? Yun ang sagot natin. Okay. So, decision, since the computed value f equals 0.64 is in the non-rejection region, do not reject h sub 0. Thus, there is insufficient evidence that the population variances differ. Okay? The population variances of the abrasive wear measurements of the two materials are considered equal based sa ating test. Therefore, the assumption that population variances are equal is justified. No? So, yun ang ating conclusion. Justified siya. No? Na yung assumption ng dalawang population variances are equal. Okay, so that's it. I hope you get it. So, good day everyone.